Conduction. All right, the first thing is flux. This guy is flux. That's the magnetic field. That's the area. And that's the angle between the area and the magnetic field. Now, we've got to carefully define that, right? So if I've got some area here, okay, the area is actually defined as a vector that is perpendicular to this thing, right? So this is the area vector. In physics is defined that way, right? So the bigger the area, the longer the vector. And this works pretty well, right? Because surfaces, if you touch something, it's going to exert a force that's in that direction, right? We exert forces perpendicular to our surfaces, right? Okay. So if I've got a magnetic field, let's change the color here. This thing really is, this computer's maxed out. Let's imagine that we've got a magnetic field it's not going straight up like this, but maybe it's at some angle like that, right? You could imagine that, right? Okay, we got to do a angle like that, right? So if the magnetic field were, say, this way, totally horizontal, the angle would be 90 degrees. We'd have no flux, right? So one way to think about flux is that it's the amount. If this was a window and the magnetic field was light, it's how much light shines through that window, that piece of area that you have. And people use these for like solar panel calculations, right? What angle do you put the solar panels at? Well, ideally you maximize the flux, the solar flux in this case, not the magnetic flux. But anyway, there it is, right? Okay, that's how you calculate the flux through something, right? And then of course that's related to the inducted, the EMF that's inducted. Okay. And there's some arcane difference between EMF and voltage, and I could never understand it. So when you guys go to college, you can come back and understand. But you can divide EMF by resistance and get current. So there it is, right? I think it's like a subjunctive. I don't know. Maybe I'm smart enough now to understand it. But this is the idea, right? Is that it's the rate change of flux is what is the EMF, right? So if I've got this coil like this, right, that has some cross-sectional area, right? It's got n number of windings, right? And there's some magnetic field here. And usually we can change the flux in a lot of different ways, right? We can change the area that's inside the magnetic field. We can change the magnetic field, or we can, God forbid, change the angle that it makes, right? Let's imagine in this case that we're just changing the magnetic field. So we got some magnetic field going through this coil, right? Okay, and then there's a change in the magnetic field. Then our EMF is going to be N times B times A. The angle here is 0 degrees. So cos of 0 is just 1, right? And then there's a minus sign. I'll just sort of keep that there, right? And then divided by the time it takes. And then in this case, maybe the magnetic field changes, right? Okay, and then divide by the time it takes to change, right? Okay, so just be careful. In general, it's going to be B1A1 cos theta 1, or I'll say 2, right? It's always the final minus the initial, right? Minus B1A1 cos theta 1, right, over the time. I mean, God forbid they give you one where the magnetic field, the area, and the angle change, right? You'd have to do this. Generally, though, it's just one thing that's going to change. Either probably not the number of windings, but the area, right? We're going to pull it out of the area, and then the time, like that. Okay. And then the minus sign is Lenz's law. So just remember that the current is going to flow to create a magnetic field that resists the change in flux. Okay, so if you lose flux, you'll replace it. And if you gain flux, you will oppose it. Okay, just always think you're always resisting the change. Okay, and ultimately that's just conservation of energy. Let me give you an example. So let's imagine I've got a wire like this, right? And the thing comes down here, and we can attach this to a voltmeter. a galvanometer, right? Okay, and then I take a North Pole magnet, and the North Pole magnet approaches that side. Well, this thing here doesn't want that magnet to approach. So one way to think about it is it'll actually resist the approach of that magnet. So this side of this coil, current's going to flow so that this side becomes a North Pole magnet and this side is south. And the way to do that is to have current go down the front. Okay, the current's going to go down the front of that magnet to resist the oncoming magnet, right? Another way, though, to think about it, right, is that the magnetic flux lines go from north to south, right? So they're doing this. And so as this magnet approaches, it's increasing the flux that way, right? The flux is increasing, and it's going to be to the left. And so what this thing's going to do is it's going to create flux to the right, because these flux lines go this way. It's one of Maxwell's laws, right? Is that the magnetic fields always loop around. Okay. So this guy's just going to oppose it. It's going to create an opposing flux. Okay. Anyway, that's Lenz's law. I'm not going to try to reteach the whole thing here, but that's it, right? And then of course, if I move this thing back and forth, we'll get a nice alternating current there. Okay. And then this last one here is the EMF induced on a moving conductor. So let's look at that. Let's imagine that we've got that magnetic field out of the page here. Let's imagine that we've got a piece of this conductor and it's L long. Let's imagine it's moving that way. Okay. The velocity, this is the velocity, right? So the velocity it's moving at, the length and the magnetic field, all you just multiply them together. And then, hopefully your wire is perpendicular to it, because that's the way they've set this up. Okay. If it's not perpendicular to it, then, obviously we got to be more clever than this, right? Now, the direction of which end's positive, what I always do is I pretend to be a positive charge riding along on this, okay? So if I'm a positive charge and I'm moving up that page, I put my index finger in the direction of the velocity, middle finger in this case out of the page. Positive charge is going to go to the right side of this. And by subtraction, the negative charge. Now, by the way, exactly the opposite happens, right? Positive charges don't move, negative charges do, but it doesn't matter, except for the Hall effect, okay? Generally, the calculations are the same. I think that's all you have to say about this.